So when they take this 116 pounds of methamphetamine to the lab, and let's say there's one particular scientist in that lab that only works in kilograms. How will we convert that? What do we need in order to convert pounds into kilograms? Anybody? How do we convert from one unit to another? All right, don't all speak out at once now. We don't want the internet to crash.
You need the conversion rate?
You need a conversion factor. Good. You need a conversion factor. Need a conversion factor. For pounds to kilograms, the conversion factor is 1 kilogram is equal to 2.2 pounds. Let me fix this. So 1 kilogram is 2.2 pounds. If I wanted to take those pounds and convert them into kilograms, I'll start out by taking the pounds, 116 pounds times the conversion factor. What do I want in the top? The number I want to keep or the number I want to get rid of? Which one of those numbers do I want in the top? Do I want to put pounds up here?
No, you want to put kilograms.
You want kilograms up top because otherwise you'll have a square of the unit, right? And we don't want that. So we want 1 kilogram over 2.2 pounds. So that pounds will cancel. Anytime you're trying to convert between units, you want to make sure that the unit that you're converting to is in the top. So here you want, this is my desired unit. And down here is, we'll call it the discarded unit. So what I want to keep, I put in the top. What I want to get rid of, I put in the bottom so that the two would cancel. All right. So now it's just a simple operation of dividing and saying 116 divided by 2.2. Can somebody do that calculation for me real quick?
52.72.
Come on with it. 52.72. Excellent.
I mean, unless you go round it, then it would be 73.
Well, we're going to do more than round it, right? Because we need to make sure that we have the correct number of sig figs. Is that right?
Yeah.
So we're going to have to round anyway. So when you're doing division or multiplication, what's the rule for sig figs? Anyway.
The same number after the decimal has to be congruent with the original start decimal.
Hold up 1 second. So for sig figs, for division and multiplication, don't we keep the smallest number of sig figs? Is that right?
Yes.
Yeah. So we keep the smallest number of significant figures. So of the two numbers that are divided here, which one has the least number of sig figs?
2.2.
2.2, yeah.
Yes. Right, so the 2.2, this has two significant figures, is that right? All right, so the answer needs to be how many sig figs?
Two.
All right, so here the 2 is not going to cause that 7 to go up, right? We'll leave it. So we can take that and say 52 point, not 55.7. And then we can take that, and because this number is greater than 5, we can round that 2 up. All right, this, hold up, let me zoom out. And need to shrink that down just a tad. All right, so that's 7. Anytime the number that follows another number is greater than 5, we round, or 5 or greater, we round up. Less than 5, we round down. So here, this number here is going to cause us to round this number up. So the answer with the correct number of sig figs is 53 kilograms. All right, any questions? So we used this example. We looked at a unit conversion. And I apologize. That's my daughter is texting me. She's watching a video about Beneful dog food, and now she's concerned because Beneful had arsenic in it. So now she thinks the dog is sick, but he's not. So let me turn my ringer down. All right. So we looked at a unit conversion. We looked at using a conversion factor. We looked at significant figures and maintaining the proper number of significant figures. And we also have a way now to convert between any units. Now, let me ask this question. We got one other piece to this problem that we can talk about, and that is the fact that the unit kilograms, so we got 53 kilograms. That's a lot of meth, by the way. That's a whole lot of meth. That's some Walter White action right there. So 53 kilograms. What does the kilo prefix mean?
$1,000.
It's 1,000. 10 to the third. I keep wanting to write a capital K, so excuse me on that. So it's 10 to the third. So how many grams is this? How many grams? So if we take the 53 kilograms, there's 1,000 grams in every kilogram. How many grams is that?
53,000.
53,000. Excellent. All right, here we go again with these sig figs. So the multiplication part, this is 2 sig figs. This is 1. Is that right? So that first non-zero digit is, I don't know, I talked about this with the second section, but there's a method like that we talked about the other day, the Pacific method and the Atlantic method. So with the Pacific method, it uses the oceans, right? To let me see if I can bring that picture in here. Hold up. Let me grab this picture and see if I can put it in this document just so I can show you what I'm talking about. Where me find my gallery. It's right here. I'm gonna bring that into this document and then I'll show you what I'm talking about. So let me grab that. Yeah, we talked about this in recitation with the second section yesterday, and I thought it was a pretty neat example. So when you're doing significant figures, if you have a number without a decimal, you use what's called the Atlantic method. So for that 1,000, and you can see here, this is the Atlantic Ocean. And then this is the Pacific Ocean. All right. So with the Atlantic method, if there's no decimal, we go from, if there's a number like 1,000, we go through that number, through every zero. Well, we go through until we get to the first non-zero digit. And so in this particular case, when we go through the zeros, the 1 right here is the first non-zero digit. So that means that in that number, there is 1 sig fig. Are y'all following that? Any questions about that?
No, it makes sense.
All right. And so with the 53, also it's the same method because there's no decimal. So that's 2 sig figs. So our answer needs to be in 1 significant figure. So this is 53,000 grams. Right? How do we write that with 1 sig fig when there are 2 sig figs there? Right? Because if we use that Atlantic method again, we can see that we go through here. The first non-zero digit is a 3. How do we write that in with 1 significant figure?
Would you round
Okay.
like 5.0?
So for so that's good. That's good. That's good. You're right. But we also have to account for the fact that this number is in the thousands, right? So we could take this 53,000 and we could move the decimal place. Come on, pen. Here. So we'll get 5.3 times 10 to the 4th. Is that right? That's the same number. Is that right?
So we don't make the 3 a 0. We
Not
just
yet.
keep it as it is.
No.
Oh, not
Because
yet.
we still
Okay.
got 2 sig figs, so we got to get rid of 1, right? So we're going to take because the 3 is not greater than 5, not 5 or greater, we can round that number now. So it becomes what? 5 times what? 10 to the 4th grams. Does that make sense? Anybody not see that?
Can you explain why the 3 disappeared?
Because the lowest number of sig figs in this calculation is 1. Uh-oh, sorry. Right, so I need to take this number and round it either up or down depending on what the number is after the decimal. But because it's a 3, we're going to keep it. We're going to not round down, but we'll keep it at 5. It won't round up. All right, so
Are
this
we
is-
rounding? Are we doing to the 4th because of the decimal placement?
Yes, because look
Okay.
at how many times I had to move it. The decimal is here. Is that right?
Yes.
And I moved it 1, 2, 3, 4 times to put it here.
Okay.
So anytime you have a number in the 10,000s, that's going to be 10 to the 4th. If it's in the 100,000s, it'll be 10 to the 5th. If it's in the millions, it'll be 10 to the 6th. So like that. So 10 to the fourth is a 10,000 calculation, right? Because that's 53,000. It's not 5,300. If it was 5,300 and the decimal would be here, I would move it 3 times. So it'll be 5.3 times 10 to the third. And this is how we express numbers in what we call, get some room, scientific notation. I gotta shrink that, sorry. And it allows us to express numbers with the proper number of sig figs, even though the accuracy goes down. Because the more you round, the less accurate your number becomes, right? So as you round and as you drop off significant figures, the amount of uncertainty in your numbers increases and the accuracy goes down. All right, everybody okay so far? Did you think we can get all of this out of this one example? That's a lot of information and in a very simple example, converting kilograms into pounds. But again, we could weave all this stuff together and not drag it through the mud with, you know, definition after definition after definition. But the initial stuff we couldn't do that with, but this type of stuff, you can combine different lessons out of one example. And we're gonna go back to that handout and work on some of those. We're gonna work on some of those problems in the handout. All right, any questions about this, about what we've done so far? Let me put a date up here.
Okay, so I think I need to brush up. I know we talked about it, but honestly, those things always slip my mind. The sig figs, I've learned it multiple times before, and the rules never seem to stay in my head. I know the ones that aren't zero are like automatically sig figs, I think. But
Yes.
there's always zeros that come either before or after the decimals that confuse me.
Okay, so if a zero comes before a decimal, it's not significant.
Okay.
If it's after the decimal, it is significant. If it's trapped in between two numbers, it's also significant. Right. So let's go to the handout and we can look at some examples on there because we did some yesterday. Let's go back to that and let's kind of brush up on it. Let's refresh it. Let me make sure I got the right one open here. We stopped here. Is that right? I don't want to project.
I think that's right.
We stopped here. So
Mhm.
like in an example, like this one, C, you see how you got those? Let me get this, the pen. You see how you got the 2 zeros here trapped in between those other numbers?
Mhm.
So they are significant in this case.
Okay, but if they were to come after like the 2 and they're
Yes.
before the decimal, they wouldn't be.
Yes, those will be what we call trailing zeros, so they wouldn't matter.
Okay.
And like right here, the fact that you have a 0 here, you see that? But it's
Mhm.
after a decimal,
Mhm.
then it's also significant. So that decimal point, anything that comes after the decimal point is going to be a sig fig.
Right. Okay, I think we got it.
Yeah, and I'll be the first one to tell you, the rules for sig figs are really convoluted. I like the Pacific and Atlantic method because at least it gives you a way to think about it. That's very cut and dry, right? So let's do some more of these calculations and let's see if we can keep track of sig figs and all that stuff. So number 8 asks us to perform the following calculations and report each answer with the correct number of significant figures, right? So this number right here is going to be in the 10,000s. I can tell you that because 628 is 10 to the 6.28 times 10 to the second. 342 is 3.42 times 10 to the second. So your answer is going to be in the 10,000s. All right. So somebody calculate this for me real quick. I'm gonna put some room here. Anybody got it yet?
The first one,
Mhm.
214,776.
All right, let's go back up.
Yeah, that one.
Yeah. So
Two
you
hundred
said,
fourteen thousand 776.
all right, great. Thank you.
Mm-hmm.
All right. 214,776. Is that right? Now,
Yes, sir, that's right.
say again.
I said, yes, sir, that's right.
Okay. I just want to make sure. All of those are significant, aren't they? Every number in that number right there, that 214,776, every one of those numbers is significant. If we do the Atlantic method, meaning we start on the right side and we draw an arrow, the first non-zero digit is 6. So that's 6 sig figs, but that's not the right number because both of my numbers over here that I'm multiplying, both of those have how many?
3.
3 sig figs. So my answer needs to be in what? How many sig figs?
3.
3. Good. So this is what we're going to do. How can we express that number with three significant figures? We need to put it in what?
Scientific notation.
Yes, scientific notation. All right, so in scientific notation, let's just start here. Come on, app, cooperate now. It's Friday. So we're going to start at the 6 and move over until we get to this. Let's say 2.14776 times 10 to the what? 10 to the 5th. Is that right?
Yes.
Hundreds of thousands is 10 to the 5th. Thousands, 10 to the 3rd. Tens of thousands, 10 to the 4th. Millions, 10 to the 6th. So on and so forth. So now we got to round. We got to do some rounding, don't we? Because as of now, it's still 6 sig figs. We want to get to right here.
So would that make it 2.15?
Yes. Because if this 6 around a 7 to an 8, that 8 would round that 7 to an 8, and that 8 would round the 4 to a 5, right? But we need 3 sig figs, so we have to drop off the other numbers. So this is going to be 2. Come on, pen. 15 times 10 to the 5th. You see how much less accurate that number is, right? It's not as precise as the other number. The more decimal places you have, the more precise your calculation is. The less decimal places, the less precise it is. But
I have a question. Oh, I'm sorry, go ahead.
No, go right ahead.
Why didn't you take the decimal after the 4 in the original number instead of, like, why did you do it all the way to the first number instead of it?
Because this is right here is a, oh, God dang it. Sorry. I hate this app. Times 4. Let me fix that. Comma. This number is expressed as a 214,776. So that is 214,776.00000. You understand what I'm saying? So the decimal point always is all, unless it's somewhere else, it's always at the very end of the number. So when I'm trying to put that number in scientific notation, I have to start here, moving it over. Uh-oh, that didn't go so well like that. I have to move it over like that. You following?
Yeah, I'm following.
So that's why I didn't start at the 4, even though that may seem like a shortcut. And even it may still even work, but you always want to start at the very last number when you're trying to put the number in scientific notation? All right. Yes, no, maybe. All right, let's do the next one. 5.63 times 10 to the second and 7.4 times 10 to the third. Can we also add in another quick thought right here? What is this? What does this number look like if it's not in scientific notation? If I just express it as is, what does that 10 to the second mean?
That the decimal was moved 2 times in order for it to be 5.63.
Yes, excellent. So this is what, 563, is that right? If it's not in scientific notation.
It'll probably have some zeros after it.
Well, no, because the 2 here means that I moved it twice.
Oh, okay, yeah. Mhm.
So the zeros will be here after the decimal. Right?
Question
Go
about
ahead.
that.
Mhm.
The exponent, if the exponent is positive, that means that the number was
Bigger.
greater than, right,
Yeah.
greater than 1 before, okay. Before you
And
moved it.
negative, great question. Negative exponents in scientific notation indicate decimals, small numbers.
It was smaller. Great.
Positive exponents mean the number is actually bigger. So by the same token, if this was 5.63 times 10 to the minus 2, your decimal will move this way, two places. So that would be 0.0563. You following that? So the
Yes.
negative exponent, just think about it this way. If the exponent is negative, you move the decimal point to the left. If it's positive, you move it to the right.
The greater and lesser than 1 makes more sense because
You like that one better? That's fine.
Mm.
Listen, however, whatever floats your boat. But
Yes, sir.
yeah, greater, positive, lesser, negative. That's fine too. All right. So, all right, what about the other number? Not expressed in scientific notation. What is it?
7,400.
Good. So you're taking hundreds and thousands and you multiply them together, right? We're going to get a number in the hundreds of thousands. Let's see what we get. Can somebody calculate that? Actually,
I got 4 million.
millions. I apologize for that. Hundreds and thousands. When you multiply them, you'll get in the million, a number in the million. You said 4 million?
Yeah. I got 4,166,200.
200. Is that right? How many sig figs is that? Let's go to the Atlantic method. We put an arrow through here. First non-zero digit is at 2. So that is 1, 2, 3, 4, 5 sig figs. Is that right?
That's what I got. 5 sig figs.
So it's 5 sig figs. All right, we need to get that to how many? 2, because the 7.4 right here is 2 sig figs. Is that right? Yes, no, maybe.
Yes.
Yeah, we want to, it's a multiplication problem. So we want to keep the smallest number of sig figs. So that's going to be, let's start at the back. 1, 2, come on, Russell, tighten up. It's Friday. I'll just rewrite it. 6, 6, 200. So on here, 2, 3, 4, 5, 6. So 4.1662 times 10 to the 6th. Is that right? Because we moved that decimal 6 times to get it where it is. Now, what do we need to do in order to get that to 2 sig figs?
You need to round that 1 to a 2.
Round the 1 up to a 2. The 2 is not going to change the 6 next to it. The 6 is going to change this to a 7. And that 7 is going to change that 1 to, it's going to cause it to round up to a 2. So we end up with this 4.2. I'll just write it over here. Times 10 to the 6. Right? Again, that is a less precise number than the one we had when we first multiplied those two together. Again, the less decimal places you have, the more uncertainty you have. All right, let's go down and start and look at some of these. I'm gonna leave these right here. I want you to work on these before you turn this in. I want you to work on these on your own prior to turning this in. And let's go to some of these other calculations. Let's do number 10 real quick, because that'll help us close out accuracy and precision. So accuracy deals with what? Somebody help me.
How close a value is to its true value.
Right. How close a number is to its to a what's the word I'm looking for? I'm drawing a blank. To an accepted standard value, right? So how close a number is to a standard value. And I need to fix that. Well, I can erase it. I'll fix this before I post it, because I'm going to post these notes in Blackboard. Right. So accuracy deals with the closeness of a number to an accepted value, and precision deals with how close numbers are together. Right. So this is another depiction of that, right? Where you have this as accurate and precise, where the accepted value is the middle of the bullseye, and you have numbers that are very close together to each other, and they hit that bullseye pretty close too. This is accurate, but not precise, meaning I'm somewhere in the ballpark of the bullseye, but I'm not really, but my numbers are not very close together. This is neither. Notice how the data points are all over the place. And this is very precise, but inaccurate. All right. So let's go down here. Checking for consistency in the weight of chocolate chip cookies. Do we know the standard weight of a chocolate chip cookie? To compare these two. All right, so we got 17.27 grams, 13.05 grams, 19.46 grams, and 16.92 grams. But we really don't know the weight of a cookie to compare that to. Right, so those numbers are imprecise because of the distance between them. And they're also, we don't know how accurate they are because we have nothing to compare that to. So we're going to say that this is both neither accurate nor precise. So we don't have a standard. All right, what about B, letter B? It says testing the volume of a batch of 25 ml pipettes. So there's my standard 25 mils. And my numbers are 27.02, 26.99, 26.97, 27.01. What do you think? It's only 2 milliliters off, so it's not a huge gap between the standard and my measurements, but those numbers are also very close to each other. Is that right? 27, 26.9, 26.97, and 27.01. What do you think? Precise, accurate, both, neither?
I say both.
Both. Good. All right. The precision is the distance between the actual data points, which is very low. And then the accuracy is the closeness of that to that 25 milliliters. So these numbers are both accurate and precise. And then for C, look at these numbers. What do you think? Determining the purity of gold. So that's my standard. So my standard is 100%. If it's a 100% pure and I'm testing the purity and these are the data points I get, what do you think? How precise are they? Like if we round it up, every one of those would round up to 100%. Is that right? So this is also both accurate and precise. All right, let's do number 11 because this is a conversion that we can work on. Right, so somebody read that question for me. Anybody?
Number 11.
Yes.
Okay, it says the label on a soft drink bottle gives the volume in 2 units, 2.0 liters, I imagine, and
Mhm.
67.6 fluid ounce. Uses information to derive a conversion factor between the English and metric units. How many significant figures can you justify in your conversion factor?
Great. Okay, so here's the question. We have 2 units and they're equivalent. So when it says the soft drink bottle has the volume in 2 units, if it has 2.0 liters and 67.6 fluid ounces, that means that those numbers are equivalent, right? So what is my conversion factor? If I wanted to go from liters to fluid ounces or fluid ounces to liters, I would use this number, right? So let's say in building a conversion factor, I'll put the liters on top and then the 67.6 fluid ounces on the bottom, right? How many sig figs are in the 2.0 liters? Again, there's a decimal, so we got to use that Pacific method. And we run into the first non-zero digit here at the 2. Same thing down here. So how many sig figs are in each one of those?
2 and 3.
Okay, good. So this is 2 sig figs. This is 3 sig figs. So when we do that calculation, what must the conversion factor be? How many sig figs? If it's a division problem. It's got to be, go ahead. I hear somebody getting ready to help us, save us.
It would be 2.
It's got to be 2, right? Because in a division and multiplication problem, you keep the lowest number of sig figs, right? So somebody tell me what the answer to that is. First of all, let's get the answer first, and then we'll go ahead, Saxton.
I'm confused, Dr. Russell.
Okay, go ahead. Ask your question. What's your question?
2.0 is 2 sig figs and not just
Yes.
1?
It's because of the decimal point. So
Oh, I thought we said the 0 behind the decimal.
no, we said that counts.
Oh,
If there's a decimal, then the zeros behind that decimal count.
okay, so just 1 0 behind the decimal.
Mhm.
One.
So that 0 is significant because of the decimal point.
Okay.
You act like you don't trust me. Like
I was just about to say,
I'm
I'm
trustworthy.
trusting you.
Yeah, just trust me. All right. So 2 sig figs. Does anybody have that calculation?
I got 0.029586.
You said 0.29586.
Yes.
And we got to get that to 2 sig figs. Right. So this is the where we'll start. So first of all, we can round that up to 0.03. Is that right?
Yes.
So then we can move the decimal here. So we can write this as 3. Dang it. Running out of space. So 3.0 times 10 to the minus 2 liters per 1 fluid ounce. And let me circle that. And that gives me to an answer with the correct number of significant figures like the problem asked for, because it says how many sig figs can we justify. And the fact that we had the lowest number as 2 sig figs, our conversion factor has that being 2 sig figs also. Are y'all following? Anybody not following that? Do you see how I got the negative exponent? Who was that asking about the negative and positive?
That was me.
Okay. Do you see that? Why is -2?
Oh yes, because we came from 0.03.
Mm-hmm.
And then yeah, I got it.
All right. Any questions about that? Let's do a couple of these conversions down here. Let's do some of these conversions down here. Let's take let's do I don't want to do that in red. So let's take A. Let's do C. Let's do G and E. We got about 2 minutes left. Let me put some space here. All right. So with A, what are we doing? We are converting from what? Grams to milligrams. Is that right? So here's a rule of thumb. Anytime you're going from, and remember milli, that prefix is 1/1000th, right? So anytime I'm going from a larger unit to a smaller unit, the number is going to get bigger. If I'm going from a larger unit to a smaller unit, the number that I'm converting to is going to get bigger. If I'm going from a small unit to a large unit, the number is going to decrease. All right. So let me write that somewhere up in here. If I go from a larger unit to a smaller unit, the quantity or the value increases. Come on, Harold. All right. And then by the same token, if I go from smaller to larger, the value is going to decrease. All right, so let's take number one. It says 612 grams, and this is a good place to really hone in on these conversion factors. How many milligrams are in 1 gram? If a milligram is, the milli is 10 to the minus 3 grams, right? So 1,000. So for every 1,000 milligrams is 1 gram. Following? So when that milli, 1/1000th of a gram, when you see that prefix, there are 1,000 milligrams in every 1 gram. We following? Anybody not see that?
I see it.
All right.
I'm just still
So,
trying to figure
go ahead.
out. No, I see it. I'm just talking to myself out loud.
Okay, that's cool. What's the answer? And let's put it in the correct number of sig figs. Is that right? 612,000 milligrams. Yes, no?
Yes,
Yeah.
that's right.
How many sig figs do I need?
3.
This is 1,000. How many sig figs are in that number? 1,000.
1.
1 sig fig here, 3 here. It's a multiplication, right? So I need to get this down to 1 sig fig. So how do I do it? 6 times what?
10 to the 5th.
10 to the 5th milligrams. Yep. 6 times 10 to the 5th milligrams. Good. So you see how the sig fig information we started with up top, how we can filter that down through all of these other calculations. All right. Let's do, we got a minute. Shucks. Let's do one more. Let's do C. Let me put some more room here. Yeah, what? All right, let's do C. What are we converting from?
Micrograms.
Micrograms, good, which is 1/1,000,000th of a gram. So let me get my pen back. I have 3,779 micrograms times, and I want to convert that to grams. 1 gram, which I'm putting in the top. Notice what I want to keep, I put in the top. What I want to get rid of, I put in the bottom. 1 gram over what?
1,000,000 milligrams.
1,000,000
or
micrograms. 1 times 10 to the 6 micrograms. Notice I'm going now from smaller to larger. So that means that my number is going to be very small. It's going to decrease. I'm sorry, not -6. It should be 10 to the 6. All right. Can somebody calculate that? Just divide. I don't want to write 1,000,000 out, so I just put it in scientific notation. But if you take that number and divide by 1,000,000, what are you going to get? Does anybody have that? 1, 2, 3.
I got 0.003779.
Mhm.
Yep.
Yep. And when we look at this calculation, we got to get that down to 1 sig fig. Is that right?
What are you asking?
I'm saying we have to get this down to 1 significant figure based on the conversion.
Okay.
Because the 1 gram, one times 10 to the 6, all both of those numbers are 1 sig fig. Is that right?
Mm-hmm.
So didn't try to do that. How do we do that?
You're going to
Move this over,
decimal
move it over,
3 and
move it over,
7.
right?
Then
So it's be 3.8
right.
times 10 to the minus 3 grams. But then we need to round that because we need 1 sig fig. So it really would be 4 times 10 to the minus 3 grams. You following?
Yep, I'm with you.
All right. So that's a good little kind of entree into sig figs and treatment of mathematical calculations, which is a big section in chapter 1. But I figured it would be much better to actually just lay hands on this. So what we're gonna do, because I really want to go through these calculations. What did I just do? What we're gonna do is, I don't know what just happened there. But what we're gonna do is we're gonna finish this on Monday. So go ahead, Ortega. How do you pronounce your first name?
It's Faraluz.
Faraluz. Okay. What does it mean? I know lose is light. What's the prefix part mean?
So Farah is one of my grandmother's names,
Okay.
and then the other name is Luz Mila, so they just put them together.
Ah, okay. Okay. Go ahead. What's your question?
So my question for the last part that you just did, how do you know when to stop? Like when you're rounding it up?
Let me see. So when you say stop, what do you mean by that?
So when you took the decimal and moved it over 3 spaces.
Yes, that's how I know when to stop, because I'm trying to get this to 1 sig fig, and if I'm writing any number in scientific notation, it is a 1 decimal number. I don't want to write 38 times 10 to the minus 2 or 377 times 10 to the minus 1. I want it in that with that 1 decimal point right there.
Okay, that makes sense. Okay, thank you.
Yeah, great question. So I just move it behind the first non-zero digit.
The rule that I previously learned was like it has to be greater than 1 but less than 10. So you can't make it 2 digits.
Right. That's good. I like that. Greater than 1 but less than 10. Right. But for me, when I see that, I just want to move that decimal point behind the first non-zero digit, and that way I know I have a number that is, again, like you said, greater than 1 but less than 10. Yeah, thank you for adding that. I like that. Where this get doubled up right there. Anyway, all right, we got to stop because we over time, and I apologize for that. But I think this was a good class, very engaging, and I appreciate all of your participation. And I hope you have a wonderful weekend and get lots of rest, get some sunshine, and all that good stuff. And we'll be back on Monday. We're gonna finish this handout, and then we're gonna move into chapter 2, which is dealing with atoms and elements. We're gonna really dig into the nuts and bolts about atoms and elements. All right, everybody good?
Thank you, Dr. Russell. Yes, sir.
All right,
Thank
problem.
you.
No problem. Thank
Thank
y'all.
you. Have a blessed one.
Thank you. Have a blessed one.
All right, do the same. Thank you.
Thank you.
All right.
See you later.
All right.
Dr. Russell, the recitation from yesterday, I did miss it. Is it still on? Is it posted on Blackboard?
You mean the form, the document that we were using?
No, I got the form. I downloaded that yesterday, but I didn't know if you guys had went over the first part of the.
Oh yeah. Look in the it's not on Blackboard, it's on YouTube, but I sent an announcement with the link in it.
Okay, I did watch some of that. Okay.
That's what we did yesterday. that link.
Okay.
That I sent. I think I sent it out yesterday evening.
Okay, I'll double check.
Mhm.
Thank you. Have a good one.
All right, you too.